Chapter 3, Biological Foundations of Behavior. So our first step is to talk about our building blocks of our nervous system, and these are our neurons. So neurons are specialized cells that make up our nervous system. And so we have a little diagram of a neuron here. For our purposes, we're going to stick to a pretty standardized, simple version of a neuron. But if you've taken a biology course or a neuroscience course, there are lots of specialized types of neurons. And we won't go into those for this class. Just know that they exist. And so each neuron has three major parts. So we have our cell body, which is sometimes called the soma. And these are all of the structures that keep a cell alive. So in biology class in high school, when they were talking about the cell and all of your organelles and all of the stuff that makes a cell function, that's all contained within the cell body. So we mostly care about the nucleus within this cell body. And I'm going to flip to the next slide to just show you what we're talking about. So our cell body is this portion, the body or the big fat part of our neuron. So this is our cell body. This is our soma. Our next thing, or our next part of a neuron, are the dendrites. And these are branches that extend from the cell body. And our dendrites receive signals. So our dendrites are like satellite antennas picking up signals from other neurons. And again, we can swap over to here, and these branchy protrusions are dendrites. And they kind of look like trees or branches. And dendrite is actually derived from, I believe it's the Latin for branch. So that's why they're named that. And so if these are receiving a signal, we can already kind of see these arrows showing directionality. But if the dendrites are bringing in a signal, and then the signal travels outward, we then come to our third portion of our neuron, and this is the axon. And an axon conducts electrical impulses away from the soma or the cell body. And so that's that motion this way, away from the cell body and towards the end of our axons or the axon terminals. It is where the axons terminate or end. And we'll come back to some of these other portions here, actually right away on the next slide. So next we're going to talk about the support system that's helping out our neurons. And these are our glial cells. And our glial cells help hold our neurons in place. So neurons existing throughout our body, they need to be held in place. They need to be guided into place as they're forming. And that support system comes from these glial cells. Glial cells also help make and move nutrients. So they're going to produce different chemicals that our neurons need to exist. And they can also move those nutrients around, so bring in good nutrients and get rid of chemical waste products. And these glial cells, with all of the different functions that they serve, also make up what's called the myelin sheath, which is actually what I was just pointing out over here. So these little hot dog bun looking, I guess, pieces on the side of our axon, these are the myelin sheath. And these are basically little buildups of fatty tissue that surround our axon. And these are really useful because they help that electrical signal that's traveling down the axon towards the axon terminals. The myelin sheath and that insulating fat helps that signal travel faster. And we'll talk about how that happens when we actually start talking about how an electrical impulse is carried through the cell. So our glial cells are structural. They're also giving nutrients and moving stuff around. They're forming that myelin sheath to help insulate and allow transmission of signals along the axon. And the glial cells remove toxins. So they're especially common in the blood-brain barrier, which helps take out and remove toxins around our brain. And our brains are one of the most dense buildups of neurons in our entire body. So we need lots of glial cells and lots of toxin removal to keep our neurons functioning in that area. So we've already kind of hinted that our neurons are sending electrical impulses. And that's one of the two basic functions that a neuron is going to provide. So these two functions, the first is generating those electrical impulses. They generate electricity in the form of a chemical charge disequilibrium. And that electrical impulse is going to create what we call nerve impulses. Now, these nerve impulses, this electrical signal, is what happens as that signal comes into our dendrites, travels through our soma or our cell body, and travels down the axon to the axon terminals. That part is a nerve impulse. But if this neuron wants to talk to another neuron, if it's going to send a signal from these axon terminals to the dendrites of the next neuron in the chain, then it actually uses something other than that electrical signal. It'll switch over and actually use chemical signals. So a neuron will release chemicals, and those chemicals allow it to communicate with other cells. So specifically, our axon terminals will release chemicals that will send a signal to the dendrites of the next neuron in the chain. And again, we'll talk about all of the details of that for each, actually, as this chapter progresses. So for these neural impulses, these electrical signals, we can talk about them a couple of different ways. Clearly, I've already called them neural impulses and electrical signals. You can also call it cell activation or neuron activation or neuron firing. And so all of these terms, all of this terminology is applying to the same process. And this is the process of producing an action potential. So we're going to walk through this whole process a couple of times in a couple of different ways, because it is one of those conceptually challenging things if you haven't learned it before. So if you know what an action potential is, then you can kind of tune out a little bit. But for everyone else, we're going to go through it nice and slow and make sure that everybody grasps the concept. So this activation, this firing, we're going to talk about it in terms of 3 different steps. So our first step is when the cell is at rest. So the cell is on its own, there's nothing going on. This is prior to activation. The cell is rest. And when the cell is at rest, it has an electrical resting potential. And we'll show a diagram of this in just a minute. But what we're saying is that inside of the cell is a slightly different charge than outside of the cell. And if you know anything about ions and charges, those ions would much rather be spread out evenly so that there's no difference in charge anywhere. So by having a different charge inside and outside the cell, we've created this tension, this electrical potential for energy, but it's resting because we're not allowing it to move. The cell membrane is keeping everything separate, so there's this potential for the electrical charges to move, but when the cell is at rest, the electrical charges are stuck where they are. So step one is that nothing is happening. We're at this state of rest. Step two is when the cell is stimulated. So something is triggering this activation, and the electrical charges, the ions that were previously kept separate from each other across that cell membrane, those ions are allowed to flow across the membrane. So we're moving charged particles, these ions, from outside to inside the cell. And by having this charge move across the cell membrane, we're changing the charge of the cell. And in fact, this process happens so dramatically that we reverse the charge of our resting potential. So the point that we started at, we end up actually going in the other direction. So when we start, we have a negative charge, a negative resting potential. And after all of these charges flow across that membrane, we end up with a positive charge across the membrane. And this positive swing is producing, or is, an action potential, and sometimes again called a neural impulse. And as the cell is producing an action potential, we can say that it's firing. And so this process happens. We've created this action potential. The cell has fired or activated. And then our next step is to actually go back to where we started from. So we're going to restore that distribution of ions so that we can have our electrical resting potential once again. So the cell goes back to normal and returns to its resting state. Now that's the verbal description of it, but now I want to show you the visuals to go with it. And first we will look at just some pictures, a series of pictures with some more words, and then we'll do a video, because I find a video helps solidify everything that we're talking about. So this graph is going to be showing us all of the different steps of having a neural impulse. And so on here, we can orient ourselves. This axis is giving us the voltage in millivolts. So this is the charge across our cell membrane. And so we have -70 is an important charge. 0 is a pretty good reference point. +40 is another important reference point. And we kind of don't really care about all of the numbers in between. And then across this axis, this is just the passage of time. So time in milliseconds. So this is telling us that this whole process happens very, very quickly in just a fraction of a second. But we can start at the beginning here, and this is the cell is at rest. This is our resting potential. And so resting potential in most neurons is going to be -70 millivolts. And so we're at this stage 1. From here, the cell is at rest. So stage 2 is when the cell gets stimulated. And that happens at this point right here. So this period is when stage 2 starts and the cell is activated. And so from our description, we're saying the cell is stimulated and the electrical charges, our ions, flow across the cell membrane. So we're going to look at what's happening. So here, sodium, which is a positive ion, sodium is Na+, meaning that it has a slightly positive charge. These positive ions were outside the cell, and they start to flow inside the cell. And so if we're having positive charges enter the cell, and the cell was negative before that, as they come in, the charge of the cell starts to rise. So the more sodium comes in, the higher the charge gets, the more positive the charge gets. And so eventually, the sodium ions, there's enough of them inside the cell that they peak at the very top here, and the peak is called our action potential. This is the wave of firing, and the absolute top so the maximum positive charge that our cell hits is going to be about positive 40 millivolts. And so once we've hit that point, the cell reverses that process. So we had all of these sodium ions flowing in, and to counter that, the cell will open up some gates in the cell membrane, and they're going to let other ions flow out. And so here we're going to have our potassium ions can flow out. And the reason why the potassium ions want to leave is because potassium is another positive ion. So the symbol for potassium is K, and if it's in ionic form, potassium would be K+, again indicating that those ions are slightly positive charged. And so once we've hit this point, there are lots of positive charges inside the cell, and the cell opens up gates that are specific to potassium, and it lets the potassium leave because positive charges don't like to sit next to other positive charges. It's kind of like when you're trying to force two magnets close to each other, but both are positive and they push back. That's what's happening with these ions. So as soon as the cell opens up those potassium gates, the potassium ions leave as quickly as they can because they want to get away from the other positive ions. And so as our positive charges start to leave, you can imagine that the charge in the cell will start going down again. They'll start getting negative as all of the positive charges leave. And so these potassium ions flow out, our charge in the cell gets negative, but you'll notice that we actually go too far. So instead of coming right back to -70, which is our resting potential, we actually enter what's called the refractory period. And this is the point when there are more positive ions outside than there should be to be at our resting potential. So we've let out too many of our positive ions, and the cell is actually extra negative for just a little while. And this is important because this is when the cell is basically getting back to normal. So as it enters into this refractory period, we want to get back to our resting potential state, but we have sodium ions in when they were supposed to be out, and we have potassium ions out when they're supposed to be in. So during the refractory period, we put the ions back where they should be. So we'll use active processes, and we will push out all the sodium ions. We'll put those back outside of the cell membrane, and we'll use a process to bring in all of the sodium ions that had gotten pumped out. And as we get back to our normal balance, then we'll return to our resting potential. So we'll exit that refractory period where we are overly negative, and we'll go back to our -70. And once we get back to -70, the neuron could at any point then be triggered to fire again. But interestingly and importantly, when we're in this refractory period, when the cell is extra negative, it can't fire. We can't trigger another action potential because the cell hasn't reset yet. We haven't returned to our resting potential. So when we're in this refractory period, that part of the cell can't do anything except reset back to normal. And this keeps the cell from firing too quickly or in the wrong direction or anything like that. Now, maybe the second time through, it's making a little bit more sense. I'm hoping it's making a little bit more sense. But we have one other visual way to look at this before we even get into a video. And this is to actually look at the cell membrane and what's happening at these different stages. So think of this tube here as part of the axon of our neuron. So it's that, I can actually scroll back here. So it's this part, this sort of long tube extension of our axon heading down towards the axon terminals. And so this tube, this straw-like drawing here is looking at part of our axon. And so this is step 1 when the cell is at rest. And there's an electrical resting potential, so the charge is minus 70 millivolts inside the cell. And at this point, we're mostly caring about our sodium, the Na pluses, and our potassium, the K pluses. There are other ions involved. There are other things going on. Those are shown here as A minus. I believe those are for anions. But we're not going into the specifics of those because there's a lot of other things we could talk about with neurons and action potentials. But again, we're going to keep it nice and simple for this class. So at rest, the way that everything exists when the cell is at rest is that we have lots of these sodium ions outside. And that's what gives us the more positive charge outside the cell. Inside the cell, we have a couple of our potassium ions, a little bit of our sodium ions, and some negative ions. But compared to all of the positive charges outside, inside is not as positive, and so we consider it as negative. And so to orient ourselves, so this yellow is our cell membrane. And if you remember back to your biology classes, the cell membrane is only selectively permeable. So things can't just pass through the cell membrane. So these sodium ions can't just choose to come into the cell, and the potassium ions can't just choose to leave. They have to travel through these channels or gates. And so there are red ones specific to sodium. Obviously, they're not actually red. It's just going to help us conceptualize. So they would be the right shape for a sodium ion, and the potassium channels are the right shape for our potassium ions. But when the cell is at rest, all of those gates, all of those channels are closed, and everything just sort of sits where it is. So that's setting the stage for what's going to happen. If we enter stage 2 and our cell is stimulated, so there's some kind of stimulus, something is triggering this cell to fire, and that stimulus causes these sodium channels to open. So in our previous slide, they were all closed and all of the sodium was stuck outside. Here, the sodium channels open, and these channels only allow sodium to come into the cell. Sodium can't leave through those channels because they're not set up to work that way. And nothing else but sodium can use those channels. So they're opening up doors that only the sodium ions can use, and they can only use those channels to come into the cell. And so when this is happening, we are seeing this depolarization. So the inside of the cell used to be negative, but it's becoming less polarized because the charge is rising. So this is what's happening here as the sodium ions flow in and the charge inside the cell membrane gets higher, it gets more positive, or it depolarizes. And so those are flowing in, and that's changing what's inside. So inside becomes more positive. As soon as we hit that peak, that top point here, that action potential is occurring, and we've hit that maximum positive charge, then we're going to switch over to starting to reset. So we would start here, and so we'll see that our sodium ions are still coming in, but all the ones that were outside are inside now. And the potassium channels have now been opened up because we hit that peak, because we had the action potential happen, and now we're going to start restoring our resting potential. And so the potassium channels open and the potassium ions leave, and that's when our charge starts dropping off again. So these positive ions are leaving, the charge is going to get smaller and smaller. And then as that has left, the sodium has come in, then we're going to sort of hand wave the fact that to get back to our resting potential, there has to be an active process where these potassium ions get carried back into the cell through particular channels, and these sodium ions get carried back outside of the cell, again using other channels, and it gets us back to the point that we started at, where all the sodium's outside and the potassium is inside, and we'll return to this negative 70 millivolts resting potential. So we'll go back to where we were when we started. So one last time. So we're sitting at our resting potential. Something, a stimulus, will trigger these sodium channels to open, and these sodium ions flow in. And as those positive ions come in, the charge rises. This is our depolarization. And so as that charge rises, we're going to eventually hit the peak, our maximum voltage of positive 40 millivolts. That is our action potential. That's the point where the cell has fired. And once we hit that point, we're going to start correcting to return back to our resting potential. So our potassium channels open, and we let those positive potassium ions leave the cell, and that reduces the charge because our positive ions are leaving. Then we enter this refractory period, and this refractory period is when we are going to bring our potassium ions back inside the cell, and we're going to bring those sodium ions back outside the cell, and we're going to return to normal. So we'll slowly return to our resting potential. But during this refractory period, the cell is busy doing other things. It's too negative to fire again. So the cell can only fire when it's at its normal resting potential. So the cell will only fire when it's sitting at that minus 70 millivolts. If it's less than that, then the cell can't fire again. So in this refractory period, we can't start a new action potential until we get back to our resting potential. And that's what this slide here says. So during our absolute refractory period, during that time when the cell is extra negative, the cell can't fire again. We can't have another action potential. And that's because the cell is basically resetting to get us back to our resting potential. And this is important because having that little pause, that point where the cell can't fire again, that's going to limit how often nerve impulses can occur. So even though they happen very quickly, we can see that from this triggering of a nerve impulse to going back to our resting potential, it's probably only 3-4 milliseconds. It's a very, very quick process. But our cells then can only fire once every 4 milliseconds. And that's going to be a hard limit because there's no way to force it to fire again once the process is started until it resets completely. And that's important because it ensures our impulses are only traveling in a single direction. So it's making sure that the impulses, our action potentials, or our neuron firings, those only go in the direction from our dendrites to our axons, and always in that direction. Now, this directionality really matters because when we had looked at our diagram and we had our sort of straw shape, and we said we were looking at a part of our axon, and we had our sodium ions, and we had our potassium ions, and we were looking at sort of the process of firing, we were only looking at one piece of an axon. But as we saw in the diagram, axons are very long. And so if we were looking at firing here, and say this is the end where our cell body is with the nucleus inside and all of our dendrites at the end, doing some fantastic artwork yet again. So if this is the end with our soma, our cell body, and our dendrites, and we had looked at an action potential being produced in this part, we know that the impulses travel in the direction of the axon terminals, looking awesome as always. And so if it's only going to be going this way, you kind of want to make sure that this piece, this part of the neuron firing, you want to make sure it can't go backwards. Because if our axon is kind of like a big straw, a big open space, and we're letting ions come into and out of the cell, what's stopping an ion from traveling backwards? Well, nothing really. There's no physical barrier that keeps that ion in the same area it entered in. So these ions can move either backwards, forwards. But this is where that refractory period comes in. If we then have a new action potential happening here in this section, and the ions, those sodium ions coming in, flow backwards, those ions, that change in a charge, can stimulate or cause an action potential. But if this section just had an action potential, and it's at this point, it's in its absolute refractory period, then it doesn't matter if those sodium ions are traveling into this area. This part of the cell can't fire again. It's stuck in that absolute refractory period where it physically cannot fire again. So these ions traveling backwards don't do anything, and that's a good thing. If those ions travel forward, then that's what actually triggers our next action potential. So that's causing this triggering. And so as time goes on, the ions traveling backwards can't really do anything because you can't cause an action potential during that refractory period. But if they travel forward, then you trigger the next action potential, and then the next one, and then the next one, until you get into the axon terminals. So this absolute refractory period is what lets these action potentials only travel in a wave towards the axon terminals, but they can never travel backwards towards the dendrites. And that's why we always talk about the directionality of this signal is always going to go from the dendrites to the terminals, to the axons. And it will not change. That's sort of a rule that we can't break. For another rule, we can talk about the all or none law. And this law states that action potentials, that electrical firing, will occur at a uniform and maximal intensity, or they don't occur at all. And what that means is that this chart, this graph showing the difference from -70 to +40 and then back to -70, that's going to happen every single time. So it doesn't matter if the stimulus, if the signal that's triggering an action potential is stronger, you're still going to have the exact same shape to this curve. All of the action potentials are going to look the same. They don't change in strength, so you're not going to see one that's higher, and you're not going to see one that's lower. It's always going to be -70 to +40 and back again. And so stronger signals, so a more intense signal, isn't actually going to cause a stronger action potential. A stronger signal would cause more action potentials. So intensity of signal is gotten across by how many action potentials you see per second, or the rate of cell firing. And so I always use the example. So if we're talking about a signal, maybe we're talking about temperature. So if we are looking at a temperature, and if something is room temperature, then there isn't a whole lot of signal there, right? So we're sitting at room temperature right now. And we're going to see an action potential. It's going to get back to normal. And then eventually we'll see another action potential. And then we'll see another one. And that's just the temperature sensors in our skin telling our brain that we're sitting at room temperature. But if that temperature climbs, if it gets really hot, maybe your computer is really warm, or maybe it's just getting to be summer and the temperature is rising. That increased in temperature, that is a more intense signal, that's going to start looking like the same sized action potentials. So they're not any higher. Any differences are just me drawing them with a mouse. But instead of having these gaps in between, now we're just going to see them firing as often as they can. So a more intense signal just means that we see more action potentials in the same amount of time. But we are never, ever going to see an action potential that looks higher. This doesn't happen. Our action potentials are always uniform, and they always occur at the same intensity. You're not going to see them bigger or always going to be the same. And so a stronger signal just means more action potentials or an increased rate of cell firing.